Today we're going to talk about the halting theorem, undecidability, and some complexity notion related to this. But first I want to start with a quote from von Neumann, who was, famous mathematician, and he said that young men in mathematics, you don't understand things, you just get used to them. And the reason why this quote is relevant is because I'm going to talk about Cantor, and we're going to use Cantor diagonalization argument in proving the halting theorem. And the argument is simple, but it's one of those mind-bending arguments that you need to kind of, get used to it before one can hope to understand it. Or maybe not understand it at all. Okay, so what is the setting? What Cantor proved that one cannot count the real numbers. So formally, we have the I, which is all the interval of all real number between 0 and 1, the open interval because it's easier to work with, and we have the natural numbers, 1, 2, 3, 4, etc. You can include 0 in it if you really want to, you don't have to. And the claim is that the sizes of those two sets are not equal, right? Now one has to be very careful here because what do we mean the sizes are not equal and they're infinity? Well, the real term is that there are infinities of different order of magnitude. So in particular, one cannot map one into the other, 1 to 1 and onto. So let's start with a much easier claim that the cardinality of the natural number is smaller or equal to the cardinality of this interval I, and the proof is straightforward, right? Because all you need to do is to map the set. We have the set of natural numbers, we have the interval 0, 1, and we just need to find the mapping from this set to this set, and this mapping needs to be 1 to 1. Right? If we have such a mapping, then you can essentially, the way to think about it, you can embed the set n into the set I, and the elements I might embed, let's assume n is green, right? Green element, I map them into element to the interval I, but there are a lot of other elements that are not mapped, so I is conceptually bigger, right? Or at least not smaller. So that's the claim, and the mapping here is very easy, right? You can just map, for example, the map I, you can map it to the number 1 over I. Right? So clearly, all the integer numbers are mapped to points in the interval 0, 1, and this mapping is 1 to 1, which readily implies the claim. So the much harder claim is that they are really not equal, that they are of different cardinalities, and the basic idea is to say, no, let's assume that in fact they are of the same cardinality. Right now, what does it mean that they're in the same cardinality? It means that there is a mapping from n to I, which is 1 to 1 and onto. Right? It's essentially, you can map this set in the set n into I. In particular, you can speak about f of 1. F of 1 was going to be some real number, so let's write it down. Right? 0.173256, blah 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 blah, or whatever it is. You can write f2, 0. Blah 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 blah. I don't know, f3 might be 0, 3, 1, 4, 1, 5, 9, 2, etc., etc., and so on, right? And let's assume that in fact the claim is true. We have a 1-to-1 mapping, right? So then every number, we have the set n, we have the set I, well, which is just an interval, so let's draw in an interval. In particular, for every number in the interval I, there must be an original number in n, right? Must be number j such that f of j is exactly this number that we selected in I, if indeed this mapping f exists, right? The idea here is that two sets are equal if you can map every element in one set to an element in the other set, and it's a perfect matching. Okay, so the trick of the proof is to essentially define a number which is going to be in the set I, but cannot be mapped by f. So how are we doing it? We're going to take the numbers on the diagonal of this matrix. What matrix am I talking about? Well, I wrote down the numbers f4, f1, f2, f3, and so on, right? And I can look on the first digit of the first number, the second digit of the second number, the third digit of the third number, the fourth digit of the fourth number, and so on, right? This defines a diagonal, right? And I can define a number which is 0 point all those digits, right? It's a well-defined number, and it's in the interval 0, 1. Of course, so far, there is no contradiction. What I'm going to do, which is a bit bizarre, is that I'm going to take whatever number is written here, and I'm going to fiddle with it, right? So what I'm going to take this number, let's call it 0.d1, d2, I don't know, maybe alpha 1, alpha 2, alpha 3, and so on. And I'm going to take every one of those digits and change it, right? The rule of the game is I'm allowed to change it into any number I want, right? So if this is 1, think about, for example, just increasing it by 1. So if it's 1, I'm going to increase it to 9. Sorry, if it's 1, I'm going to increase it to 2. If it's this is 7, I'm going to increase it to 8, and so on. If it's 9, I'm going to increase it to 10, so it will be 0, right? So I can, for example, do that. The important thing is that what I got a number. Let's call this new number d1, d2, 0, sorry, 0.d1, d2, d3, and so on. I got a number, and the important thing is that every one, if I look on the ith digits of this number, right? I looked on the ith digits, so I have to go to the ith line, right? I got a number here, I got a digit here. The ith digit, whatever written there, is not the ith digit in the ith number here, right? Because that's how we defined it. We took the ith digit of the ith number and we chose something else. Find something new, right? That's what we are doing here. Every one of those digits have to find something new. So we got a number that cannot be in mapped by f, because if it was mapped to a location I, then it would be the ith row in this matrix. It means that the ith digit would be on the diagonal, but then the ith digit on the diagonal is definitely not equal to the number of this number d, because that's the way we define it, which we get a contradiction, so it's not possible, right? So that's the proof. There is a subtle issue, a subtle nasty issue with the fact that we are dealing with a decimal system. A decimal system is not unique, right? So the number 0.19, sorry, let's see, B. 0.1111, well, that's not the one I want. 0.199999, right, to infinity, this is just 0.2, right? The two numbers are the same number, they're equal. So there is not unique representation, so you have to deal with it. The only modification you need to do in the proof is that whenever I choose a digit, right? So when I choose the I digit di, I took it to be anything that is not alpha I, right? So I have 9 choices. And now I'm going to make another modification and require that the I digit is different than the previous digit I chose. So it's different than di minus 1, right? And this prevents this problem because that implies that the number we get in the end is a number that have a unique representation in the decimal system, which means that it indeed must be some row in the matrix. This is a low-level technical issue. Don't worry about it, right? The proof in the slides does, right, is written in this way, but that's, you can just ignore it, right? So So let's go back to the matrix, because this is kind of the important idea. The important idea again is that we have this matrix of digits, and we had chosen the I digit in the new number to be, any digit between 0 and 9, which is not the previous digits and not the I digit on the diagonal. And that's how we define the number, and the rest just follows. Okay. So we get a number between 0 and 1. It's a real number, but it cannot be in the matrix, because we just argued that whatever digit in this number that is hits the diagonal is different than what's written in the diagonal, which is impossible. And we conclude that our assumption that there is a mapping 1 to 1 and onto from the natural numbers to I is false, namely their cardinality is different. Okay, so by the way, I believe that you already seen this proof before in 173 and so on, but since we are using this diagonalization argument shortly for the halting theorem, I think it's good to see it again, and also at some level, as the quote in the beginning said, it's good to get used to this argument before we use it again. Okay, so here's another quote from the Hitchhiker Guide to the Galaxy about, they went to search something and they found an old man that claims everything is false and nothing was true, but then they discover later on that he was wrong. So this is kind of a mild instance of the liar paradox, which is really an instantiation of the same argument that we just used, the diagonalization argument. And the liar paradox is known as, this sentence is false, right? So if this sentence is false, then it's true. Let me try again. If the sentence says this sentence is false. Okay, if this sentence is true, then the sentence claims that it's false, then it's false. Okay. On the other hand, if the sentence is false, but the sentence says that it's false, then it's true. So it's a contradictory. So that's impossible. And this liar paradox is, well known, goes back to antiquity. Of course, there is some Indian philosopher that thought about it in 1500 years ago, because why not? And there are really not, there are interesting answers. You can look on Wikipedia page, like I did. It was an interesting read. From my mathematician point of view, the problem is that, natural language allows us to be extremely imprecise. And as such, this sentence is essentially nonsense. And then whether it's true or false is not relevant, which is kind of a way that you can get away from almost any written paradox that is in language. In turn, this is related to Russell paradox. So Russell paradox is in fact a paradox invented by Russell that was used to attack the current, set theory that was emerging in the end of the 19th century. It essentially was a set of all sets that do not contain themselves as members, and then you showed that essentially this set cannot exist. And Russell paradox was very important because it essentially made mathematicians realize that you have to be extremely careful in what you allow when you define sets, right? So in some sense, you cannot do self-reference when defining a set because of Russell paradox. And it's also remotely related to this omnipotence paradox, right? Can an omnipotent being build a stone so heavy that it cannot lift it, and so on. So this diagonalization argument is very old and very standard. And that's all I wanted to tell you now. In the next step, we will jump into the halting theorem.